Dear students, today we'll discuss on numerical problems related to three-phase, full and half-controlled rectifier fed separately excited DC motor drives. In the previous class, we have seen the operation and working principle of half and full controlled rectifier for the separately excited DC motor. There we have performed analysis of both half controlled and full controlled converters, and we have seen that these two converters can be used for one quadrant operation uh, of a DC thread. And we'll also see the determination of motor speed, back EMF, and firing angles. So we'll concentrate today on these numerical problems related to this drive. Yeah. So before going to the numerical problem, just we shall see what are the what are the equations that are required for half wave controlled converter. For half wave rectifier, we have V average is equal to 3 root 3 Vm by 2 pi into cos alpha. For full wave half controlled converter, the average output voltage is given by 3 root 3 Vm by 2 pi into 1 plus cos alpha. 3 root 3 Vm by 2 pi into 1 plus cos alpha. From that we can find I average and hence the speeds. Okay. So first let us see half controlled thyristor. Three phase half controlled thyristors. So that means it is three phase full wave half controlled thyristor bridge with 400 volts, three phase 50 hertz supply is feeding a separately excited DC motor. So supply voltage is 400 volts. So this is your line voltage RMS value. Then frequency is given. Armature resistance is 0.2 ohms and armature rated current is 100 amperes. Back EMF constant is 0.25 volts per meter. So motor specifications are given. Armature resistance is given. Rated armature current is given. IA rated is given. And back EMF constant. So we know that back EMF is given by EB is equal to KE phi into omega m. So now it is given as volts per RPM. So that's why it is Nm, okay, or N speed of the motor. So now this Ke into phi is called as the back EMF constant. So Ke into phi will be equal to what? Eb divided by Nm, that is volts per RPM. So this 0.25 represents Ke into phi. So what we have to find? Determine the no load speed, let us say N naught. If the no load armature current is 5 amperes and the firing angle is 45 degrees. So 45 degrees is the firing angle. Also determine the firing angle. So what is the firing angle? To obtain a speed of 1500 RPM at rated armature current. What is rated armature current? It is 100 amperes. So here IA is 100 amperes. Yeah. So based on that, now we'll try to solve. Yeah. So armature voltage at no load condition is VA naught is equal to 3 root 3 Vm by 2 pi into 1 plus cos alpha, as it is three phase full wave of controlled converter. Now we have to use this formula 3 root 3 Vm by 2 pi into 1 plus cos alpha. So substituting, we will get that VA average is 461 volts. So from this, once we find this VA average, I know IA naught as 5 amperes, the no load condition, and therefore we can find out what is the back EMF that is induced. EA naught will be equal to VA minus IARA, and that is equal to 460 volts. So VA average is 461 and back EMF is 460 volts. So speed at no load N naught is equal to EA by KE5, and that is equal to 1840 RPM. 1840 RPM. So back EMF developed at speed of 1500 RPM at rated speed. What is the back EMF developed? That will be 1500 into 0.25, that is 375 volts. Okay, into this one. Second question. Also determine the firing angle to obtain a speed of 1500 RPM at rated current. So at rated current, if the speed is this, what is the firing angle? No. So as the speed is 1500 RPM and the rated current, we have to now find the back EMF at this condition. Okay. So that is 375 volts. And from that we can find out VA average as 395. That is nothing but EA plus IARA. So knowing the VA average value, substituting in this equation, all values are known. So we can find out alpha. So alpha is 62.45 degrees. So if I operate the converter with alpha equal to 62.5 degrees and the motor is running at 1500 RPM, then we get the VA average as 395 volts. So now let us see a problem related to full wave fully controlled. So for full wave fully controlled converter, it is also single quadrant operation. Here the average voltage equation is given by VA average is equal to 3 root 3 Vm by pi into cos alpha, and IA average is VA average minus VA by RA, and we can substitute the VA average value or equation. For discontinuous operation, the average output voltage is given by this formula 3 root 3 Vm by pi into cos alpha plus 30 degrees minus cos alpha plus 90 degrees. So from that we can find V average and the T average, all these things. Yeah. So let's go to the problem. A three-phase full converter. Full converter means what? It is full wave, fully controlled. That means all devices are SCRs. So a three-phase full converter shown is used to control the speed of a separately excited DC motor rated at 100 kilowatts, 600 volts, 2000 RPM. The converter is connected to a three-phase 400 volts 50 hertz supply. The armature resistance RA is equal to 0.051 ohms and the armature circuit inductance is LA equal to 10 millihenry. So motor armature resistance and inductance are given. The armature voltage constant is KE5 is equal to 0.25 volts per meter. The rated armature current is 100 amperes and the no load current is 10 amperes. When the converter operates as a rectifier, see here, when the converter operates as a rectifier, and assuming that the motor is continuous and ripple free, the motor current is continuous and ripple free, determine A, the no load speed when the firing angle alpha is 60 degrees and 0 degrees and 60 degrees. So we have to find two speeds. At no load condition, if the converter is operated at 0 degrees, what is the speed? If the converter is operated at 60 degrees, what is the speed? Then B, the firing angle to obtain the rated speed of 2000 RPM at rated motor current. So at no load condition, first we'll see Vm is equal to, this is nothing but phase voltage peak value. So given is 400 volts line value divided by root 3 will give phase value RMS into root 2 will give peak value phase voltage peak value. That is nothing but Vm given by 325.22 volts. Let the converter output voltage be equal to V naught average equal to armature terminal voltage VA given by 3 root 3 Vm by pi into cos alpha. So substitute the values, then you'll get 538 into cos alpha. So for alpha is equal to 0 degrees, VA average will become 538 volts. From this, we can find out what is back EMF, V average minus IARA, that comes to 537.5 volts. No load speed can be found as N naught is equal to what? EA by KE5, and that is 2145 RPM. For alpha equal to 60 degrees, now the VA average will become 269 volts. From that, we can find out back EMF 268.4 volts, and then the speed now will be 1073.64 RPM. By doing the EA divided by K5, we will get this speed. Now, the second one is asked to find out what is the alpha at full load condition. So, at full load condition, what is back EMF? It is 500 volts and terminal voltage is 505 volts. So, therefore, we will get alpha as 20.14 degrees. So, in any case, you have to use V average equation, which gives the relation between EB and the alpha. So, from that, we have to find out the remaining values. Okay. One more problem. A three-phase, three-pulse converter. Three-phase, three-pulse converter means what? Three-pulse means it is half-wave rectifier. Okay. Three-pulse half-wave rectifier feeds an RLE load having resistance of 2.5 ohms. Okay, this is armature resistance of the motor and inductance causing perfect smoothing and a negative voltage of 250 volts. The converter is supplied from a three-phase balanced supply at 50 hertz and line to neutral voltage of 150 volts. So determine the mean value of load current at a firing angle of 120 degrees, average thyristor current, RMS value of thyristor current. So now for a three pulse converter, we have V average is equal to what? 3 root 3 Vm by 2 pi into cos alpha. So now for the first condition, find the mean value of load current is there. So for that we should have what is the average voltage for this alpha. So based on that, substitute alpha and Vm value, you will get VA average as minus 87.71 volts. So therefore, the current is equal to VA average minus EB by RA, that comes to 64.92 amperes. And another one is what is average thyristor current. The load average value is 64.92 amperes as three thyristors conduct for 120 degrees, so that each thyristor average current will be equal to IA average divided by 3, and that is equal to 21.64 amperes. Then coming to thyristor RMS current, IT RMS is given by total IA average divided by root 3, and that is equal to 17.22 amperes. Yeah, dear students, we have seen and made use of the average voltage, back EMF and torque equations, and based on the quadrants of operation, we should be able to find the firing angle, speed, back EMF of three-phase, full and half controlled converters, excited of separately excited DC motor drive. We have also seen an example for three-phase half-wave controlled DC drive. Yeah, so this is the outcome. I have shared some of the additional questions so that you can solve them. Please solve these problems. So you can refer chapter 5 of GK today, 5.12 and 5.13 section, and go through the solved example 5.17. Then solve the exercise problems 5.43 and 5.44. Dear students, thank you.